able to recover back the original baseband signal. Now let us see some example. At least one example. Let us see what will be the problem. So to see that example, let us say that the local oscillator is 90 degree out of phase with the transmitted signal. The transmitted signal is having a carrier. The carrier is 2 times cosine 2 pi f0t. Since the local oscillator is 90 degree out of phase, if you take cos theta, 90 degree out of phase from cos theta is sin theta. So the signal generated by the local oscillator is 2 sin 2 pi f0t. That is the signal generated by the local oscillator. Now if that happens, yt, zt will now be equal to yt into 2 times sin 2 pi f0t. Yt is equal to 2 times xt into cosine 2 pi f0t. So if you multiply that, then zt is equal to 4 times xt into cosine 2 pi f0t into sin 2 pi f0t, which is of the form cos theta into sin theta. Cos theta into sin theta is of the form 1 by 2 sin 2 theta. So this will be 2 times xt into sin 2 pi of 2 f0. Now this signal zt, which is equal to 2xt sin 2 pi 2 f0, from that there is no method of recovering xt, because if you use the low pass filter, this whole part will be filtered out, leaving out a zero output. Receiver output will be 0, or if there is a DC term, it will be only DC. So this, if you look at the picture here for the receiver outline is a straight line, red line 0 indicating. So this is the worst case. Which means if the local oscillator is 90 degree out of phase, then we cannot receive the signal. This is the worst case scenario. If the receiver, local oscillator and carrier frequency are phase shifted by 90 degree with respect to each other. In this case, we cannot recover the desired baseband signal. It is not possible. So this is one instance. So similarly, you can take other instances and see that it is difficult to recover back the original signal. Let us look at the scenario in the frequency domain or in the spectral domain, frequency or spectral. In the frequency domain is also called the spectral domain. The reason is the amplitudes at discrete frequencies are called spectrum. So the discrete frequencies are continuous frequency. Amplitudes are different frequencies. The curve that gives you the amplitude at different frequencies is called spectrum. So this domain, frequency domain, is also called the spectral domain. Now the top figure, or the transmitter output, we are not going to discuss. The output for the receiver, if you look at the receiver output, you see we have for the local oscillator 2 sine 2 pi f0t. And now 2 sine 2 pi f0t, if you consider it, its Fourier transform, then we have the two values. One will go to f1, one will go to minus f1. But since sine minus theta is equal to minus sine theta, so at these 2 points the amplitudes will be inverted. At minus f1 the amplitude will be positive, at f1 the amplitude will be negative. Because the amplitudes are inverted, the signal or the transmitted output at these amplitudes, when you multiply them with these amplitudes, they will also be inverted. So when they are translated to 0 original frequency, from minus f1 side, which is translated, that will be in positive direction. From cross one side, which is translated, will be in the negative direction. They will be of same amplitude, so they will cancel out each other. So once we pass it through the low pass filter, the receiver output will be 0 because of cancellation. So this is the frequency domain view. So now let us come to the single sideband. Ssb stands for single sideband. S for single, S for side, for band. Single sideband. Now, what we saw up to now, that there are two sidebands. There is an upper sideband, there is a lower sideband of the signal which are symmetric. So, since they are symmetric, the upper sideband and the lower sideband, they are symmetric at plus minus f0. The upper sideband and lower sideband are symmetric, which means if you consider f0, on both the sides of the f0, there is a spectrum. So on left side of f0, on the right side of f0, there is a spectrum, and these two spectrums are symmetric. These two are called the sidebands, lower sideband and upper sideband. Similarly, for minus f0, on its left side, on its right side, there are two spectrums. Now, since they are symmetric, they are containing the same amount of information or the same information, which means we can do away with one of the sidebands. There are two sidebands on left side and right side. We can filter out either the left side or the right side. So if you filter out the left side or the right side, whatever is left, either left or right or left, that will contain the signal, that will contain the information. So when you translate it, we will get back the information. There won't be any problem. Standard amplitude modulators, AM is neither power efficient nor bandwidth efficient. None of this. That we have already seen. Standard AM, it is not power efficient because of the DC. So since there is a DC, that is consuming more power, so that power is unnecessary waste. Now bandwidth, it is not bandwidth efficient because we have two sidebands containing the same information. So one bandwidth is automatically, we are wasting one bandwidth. In the bandwidth, suppose it starts from minus W, goes through W0 to plus W, then minus W to W0, that bandwidth is not required. Or either minus W to W0 is not required, or W to W0 is not required. Only half will do. So bandwidth minus W to plus W, that bandwidth is a wastage. Half of that will do. So standard AM is neither power efficient nor bandwidth efficient. DSB improves the power efficiency, but still it takes up twice the necessary bandwidth. So that is also bandwidth it is not bandwidth efficient. Most of the baseband signals, they have no DC or very low frequency components. So they don't have those things. one of the sidebands can be removed at the intermediate frequency. IF stands for intermediate frequency, or RF. RF stands for radio frequency. Either of these two stages of the receiver, when you study about receivers, particularly the super heterodyne receiver or heterodyne receiver or homodyne receiver, there you will learn that once you receive the signal, then we generate an intermediate frequency. When it is multiplied with this local oscillator, then we go to RF. So those parts are done. So one sideband either at the IF or RF stage can be removed. It is easy to remove it at the IF stage, intermediate frequency stage, using a filter. IF filter design is much more easier than the RF filter design. So at the IF stage we can always remove this. Now let us look at the spectra of the Ssb signal. So original signal you can see, XF is the frequency domain representation of the signal XT, which is the baseband signal. That is, in the top you can see two hats, two red hats on both sides of 0. That is the original signal. So that is multiplied by the carrier, which is 2 cos 2 pi f0t. In the spectral domain, it is at minus f0 you will get one spectrum, and at plus f0 you will get one spectrum. Both are in the positive direction because cos minus theta is equal to cos theta. Whereas if you take sine instead of cos, then sine minus theta is equal to minus sine theta. So the negative will be in the upper direction, the positive one, the f0 will be in the lower direction, that we have seen. So this is what happens. So xt, that is multiplied by 2 cos 2 pi f0t. Then the output is no more yt there. So the output is not transmitted. So this is where we are dealing with this. Then we are using a sideband filter. So we filter out one sideband. Because of this, we will filter out one sideband. The other sideband will be intact. That will be our yt. So this is in the transmitting stage. So transmitter output of the, here we are filtering out the upper sideband. We have the lower sideband. Ssb stands for lower sideband. So transmitter output, or LSB, you can see, look at the positive f0 side. If positive f0 side, the lower sideband is present, the upper sideband is not present. What is the upper sideband? If you look at the original signal, we have two hats. The right hand hat has a value in f more than the left hand half. So the frequency for the right hand half is higher than the frequency for the left hand half, which means this one is upper. The right hand side is upper, the left hand side is lower. Here what we have done is filtered out the upper sideband, so we have the lower sideband. So transmitter output is only the lower sideband. So lower sideband is translated. So this will be translated when we say lower sideband, it will be towards the origin. So in both the cases, at f0 it is towards the origin, at minus f0 it is towards the origin. So this is the Ssb spectra. One of the sidebands has been removed by the sideband filter or phase shift technique. Signal sideband is reduced. So bandwidth, it becomes bandwidth efficient, 2 times more bandwidth we have, because bandwidth we have recovered by filtering out that bandwidth we have recovered. So in the channel we will get that much of bandwidth to transmit the signal. So 2 times more bandwidth efficient. This is Ssb spectra is 2 times more bandwidth efficient. Then we will come to the quadrature modulation, QAM. This quadrature modulation, it takes advantage of coherent receiver sensitivity to phase alignment with transmitter local oscillator. As we discussed, in case of coherent receiver, the phase of the coherent receiver must be in line with the transmitter local transmitter. So transmitter phase and the local oscillator phase, they must be same. That we have seen for the DSB coherent receiver. That advantage, we will take that advantage here. So let us consider what happens here. We essentially have two orthogonal transmission channels. In this case, quadrature multiplication is they are in phase quadrature. Quadrature indicates phase quadrature. Phase quadrature means one will be in 0 degree, other phase will be 90 degree. So the phase difference between two signals will be 90 degree. Then we call it a phase quadrature. Which is 0 degree, that we call the in phase or I. Which is 90 degree, that we call the quadrature phase or Q. So I and Q, two signals will be there. Okay. So we essentially have two orthogonal transmission channels, one for in phase I, other for quadrature phase Q. These will be available to transmission channels. This will transmit two independent baseband signals, one in I, one in Q. Because I and Q are 90 degree in phase difference, therefore because of the phase difference, through Q, using Q cannot get I. Using I, we cannot get Q. Because I will be 0 in through Q. If you receive I, it will be 0, 90 degree phase C. Through I, if I receive Q, again 90 degree phase difference, so that will also be 0. So we can use two signals simultaneously. We can transmit two different signals which are 90 degree different, whose phases are 90 degree different. So we can transmit two independent baseband signals I and Q onto two sine waves in quadrature at the transmitter. That is what is shown here. So if you look at this input IT and QT, one is a hat, other is the M. QT is M, IT is a hat. So if you look at these two, these are two different signals. They are in phase quadrature. Since they are in phase quadrature, for the first one we are multiplying. The local oscillator will be 2 cos 2 pi f0t. For the second one, it is 2 sin 2 pi f0t. They pass through there, through the modulator. Then we add them up. There is a sum or where we add them up, that gives us the YT. So once we get the YT output, we will get the transmitter output. Transmitter output, you can see the red one and purple one. They will be added up in the transmitter, but they will not cancel each other. They will be added up, and that will be what is transmitted. When we receive, we will receive them separately. The red one will be receiving by multiplying with cos 2 pi f0t, we will receive the red one. If we multiply by sin 2 pi f0t in the local oscillator, we will receive the purple one. The N we will receive if we multiply by 2 sin 2 pi f0t, and the red we will receive when we multiply by 2 cos 2 pi f0t. That is what is shown here in the receiver. We are multiplying by 2 cos pi. Look at the right hand picture. Left hand picture we have discussed. Look at the right hand picture. In the right hand picture, YT is the input. Then it is multiplied by two local oscillators. One is cos 2 pi f0t, other is 2 sin 2 pi f0t. Cos 2 pi cos 2 pi f0t, that when we multiply, that will give us the red one. So that then we pass it through low pass filter as in case of DSP. So that will give us the red one. The purple one or the M will be cancelled, 0. Similarly, when we multiply by 2 sin 2 pi f0t, then the red becomes 0. We will get the purple or M as the output. So demodulation using two sine waves in the quadrature at the receiver. it must align receiver a low signal, local oscillator signal in frequency and phase to transmitter local oscillator signal. Proper alignment allows I and Q signals to be recovered as shown in the picture as we discussed. Then let us see what is the impact of 90-degree phase misalignment. If there is a misalignment in phase, what is the impact? If there is a 90-degree phase misalignment, only impact is now a sin 2 pi f0 t will receive the m and cos 2 pi f0 t will receive the hat. That much change will occur because of the 90-degree phase misalignments. Only that much of change will occur because sin 2 pi f0 t plus 90 degrees cos pi, and similarly cos 2 pi f0 t plus 90 degrees plus minus 90 degrees sin. So that must change. So the upper one will act like the cos, lower one will act like the sin. So on that way we will get back the m and hat. So I and Q channels are swapped at the receiver if a low signal is 90 degree out of phase with transmitter. However, we do not lose any information in this case. This can use baseband signal processing to extract IQ signals despite the phase offset between the transmitter and receiver. Because we are not losing information, we are getting this gives you a simplified view of what we discussed. Assume that transmitter and receiver phases are aligned. That is the first thing that we will assume. Ideal case, low pass filter in receiver are ideal. This is also ideal case. Transmit and receive IQ signals are the same except for the scale factor. These are all ideal cases. But in practice, RF signals will add distortion, which is causing fading. They will cause fading and add distortions. Channel means after it leaves the output YT, after it leaves the transmitter, before it reaches the receiver, between these 2 points, this is called channel. The signal travels from transmitter to receiver, that is the channel. So in this case, what we will require is appropriate signal processing, like DSP or analog signal processing. So we will require appropriate signal processing in the baseband DSP used to correct these problems, the problems of distortion, problems of fading. They can be corrected using DSP. All these that we discussed come under analog modulation. This is mostly the amplitude modulation that we discussed. We'll shortly discuss about the frequency modulation, but these are amplitude modulations. Here you have this picture shows you two signals, I and Q, and we are getting back the I and Q using this. IQ signals are taken a continuous range of value in the time domain, uses AM or FM radios, amplitude modulated radio or frequency modulated radio. That is where it is used. It is used in television, not for high definition television, non-high definition televisions, and the first generation of cellular phones. Newer systems today, they typically employ digital modulation instead of analog modulation. So let us come to digital modulation technique. These will also discuss in short about digital modulation. In the digital modulation, the input to the modulator is the baseband input, but it is digital in nature. Now you can ask me how it becomes digital in nature. All signals, all natural signals that we deal are analog. Now how it can become digital in nature? You will read this when you read digital communication in practice in your class, regular class. But for the time being, remember what you have read in the school days. Not about digital communication, but remember what you have read about school days in mathematics. I am sure you learned the plotting of graphs in the school days. X will be given to you, Y will be given to you. You will take a graph paper, then find out what corresponding to each X, what is Y. Make a point on the graph paper, then join those points. So that gives you the graph, right? And that is how you have learned how to plot a graph, which means you did not know, if you consider a function, you did not know for each x value what is the y value. You knew some of the x values for which y value is given, and you plotted the graph. Or in other words, you can say that a sample of x value with corresponding y values were given to you in the schools, and from those samples you plotted the graph or plotted the plot or plotted the curve that gives you the function form of the function. That is what you have done. Here what we do is we do the reverse. The plot is given to us. We take the sample values. From the plot we take the sample values. We have something called a Nequist criteria. We take a criteria, particular criteria. Based on that criteria, we take sample values. Now once we know the sample values, a signal will be y is the amplitude of the signal, x is the time of the signal. So at different times we take the sample values, then we plot that. So you take those dots, then plot the signal. That we can do. So if I take those sample values and transmit those sample values, you receive those sample values. Then you can do the plotting, you can get back the original signal. So sampling is to be done according to a criteria. For recovering back the original signal, the sampling is to be done according to a criteria. That criteria or the Nequist criteria says if the lowest frequency contained in the signal is f, the sampling must be done at 2f. So sampling time should be 1/2f. If you do at that speed, the sampling if you do at that speed, then from the sample points we can recover the signal. So 2f is the minimum frequency of sampling. It should be more than or equal to 2f to get back the original signal. So let us have a signal. Let us take a signal, take its samples. So the signal, okay, before that, let me tell you something about, have you read digital electronics? I am sure from the plus 2 level, you are exposed to digital electronics. In the digital electronics, you use 0 or 1, high or low. Now what do you mean by high or low or 0 or 1? In electrical circuits or electronic circuits, we don't have anything called 0 or 1 or high or low. What do you mean by that? By that we mean that suppose you have a battery, 5-volt battery. We have a 5-volt battery. Then if we measure the voltage to be 5 volt, it is 1. If we measure the voltage to be 0 volt, it is 0. So 1 volt or 0, 1 or 0 correspond to 5 volt or 0. Now suppose the battery is used, a 5-volt battery has been used for some times. Now when you measure it, it is not giving you 5 volt, but it is giving you 3.5. The output is 3.5 volt. Now if the output is 3.5 volt, what will you do? Is it 0 or 1? We have decided that 0 is 0 volt and 1 is 5 volt. We have now 3.5 volt. Will it be 0 or 1? Usually we take this to be 1. Suppose the output is 1.5 volt, we take it to be 0. What we do is, between 0 and 5 volt, we fix a threshold. So below that threshold everything is 0, above that threshold everything is 1. Mostly the threshold is in between, exactly at the middle. So 0 to 5 volt means 2.5 volt. It will be above from 2.5 volt to 5 volt is 1, below 2.5 volt is 0. That is how you decide 0 and 1. Now when we consider a signal, we will do the same thing. Measure the voltage, measure the amplitude, and you decide the signal level to which it is corresponding. Suppose signal is from -5 to 5 volt. So lowest peak is -5 volt, upper peak is 5 volt. Divide that into 8 or 16 or 2 or 4. So 2 to the power n number of levels. We divide -5 to +5 into 2 to the power n number of levels. Each level, lowest level is 0, then the next level is 1, next level, the level above that is 2, that way we go. So 0, 1, 2, 4, that way we go. Now when we sample it, corresponding to the value of the sample, find out to which level it is corresponding. So the signal value will be that much value. That is what is shown here in the baseband. The dashed lines, horizontal dashed lines, are the levels, right? Now since it is discretized, the signal has been discretized, it is not no more continuous. So it is discretized, so it looks like this. The signal is at this level or that level. How the level will be fixed? Which means if it is between the lowest dashed line and the dashed line above that, in between that, if it is below the middle of that, it will be the lowest value. If it is above the middle of that, it will be the highest level. So that way it is the signal value which is nearest to one of the dashed line. That dashed line will correspond to the discrete value of the signal. So that is discrete value of the signal. So that is what is done here. So accordingly, original may be sine wave or some haphazard wave, haphazard or random signal. So if we take their samples, it will look like this. Baseband signals will look like this. We are taking 2 baseband signals here again. They are in phase quadrature, but they are discretized. So 2 discrete baseband signals. These are not digitized, discrete baseband signals. We are taking 2 discrete baseband signals, sending them through a QAM type of thing. So local oscillators, 2 local oscillators, 2 cos 2 pi f0t, 2 sin 2 pi f0t. Then whatever is the output, they are summed. So that is yt. Then yt is given as the input to the receiver. Again multiply that with 2 cos 2 pi f0t, 2 sin 2 pi f0t, 2 local oscillators. Also 2 receiving paths. Then we use the low pass filter using the baseband signal principle, the coherent receiver principle. Then we will get back the output. Received output will be similar to the baseband. So here we have in the receiver output, you can see there is a decision boundary. What we will receive, the value, whatever value we will receive, that value will be decided based on the boundary. Boundary is the dashed line. So that value which is nearer to the dashed line, it will go to that dashed line. So that is how you take. So this is the decision boundary. Then along the time we have taken the samples, therefore sample times are shown. So to summarize this discussion, let me tell you this way. Yeah, IQ signals, they take on discrete values at discrete time instants corresponding to the digital data. The receiver samples the IQ channels, uses decision boundaries to evaluate the value of data at each time instant. IQ signals may be binary, which means 0 and 1, or multi-bit. Instead of 0 and 1, it can be multi-bit. Here we have shown multi-bit signals, not binary signals. We can see different levels, 1, 2, 3, 4. 4 levels we have seen. 4 dashed lines, 4 levels. So it can be multi-bits. It also can be multi-bit. Both are possible. Now, what are the advantages of digital modulation? Why we will go to digital modulation? These advantages you will read naturally later. But let me summarize what is available. You can summarize those things. This allows information to be packetized. So information can be sent in packets. 0, 1, 1 can be 1 packet, 1, 1, 1 can be 2 packet, or 1 packet, 1, 0, 1 can be 1 packet. So this way you can packetize the information. So allows information to be packetized. So since it is possible to packetize it, we can compress information in time and efficiently send as packets through the network. So receive the packets, then arrange the packets accordingly. As per requirement, arrange the packet, then we get back the original signal. In contrast, analog signals require connections that are continuously available. So since we are sending packets, connections are not continuously available in time. So once t is equal to 0 you send, t is equal to 2 you send, t is equal to 1 is free. So in that time you can send another signal. That is possible in digital. That is not possible in analog because it is continuous. Therefore, the analog signal is an inefficient user of radio channel. If there is a dead time, when you are not sending any signal, the dead sign is also accommodated. It is also present there. There will be dead time, but you are not sending any information, but you cannot use that time in the information flow. Dead time means there is no signal. Signal is not present. So that is what is called dead time. Again, this allows error correction to be achieved. Digital error correction is much more easier compared to the analog error correction. So allows error correction to be achieved. By the process of digitization, most of the error is eliminated, most of the noise is eliminated. So it is less sensitive to radio channel imperfections. Digital signals are less sensitive to radio channel imperfections. Digital signals enables compression of information. We just discussed it. Since information can be compressed, so it is more, it can use the channel more efficiently. So more efficient use of channel is possible using digital modulation. Then it supports a wide variety of information content. Wide variety, by wide variety what we mean? We mean voice. Voice is also available in analog signal. Analog modulation. Similarly, image is also available in analog communication. Video is combination of voice and image, that is also available in analog communication. But when you come to text, email messages, all these, they require digital bits. So they are not possible in the analog signal, analog modulation. So voice, text, email message, video, all can be represented as digital bit streams. So everything can be sent using digital modulation. So that is the major advantage of digital modulation today. You are using smartphones because of digital modulation. Because digital modulation is possible, we can use smartphones where we can communicate using voice, using text, using email, using video. Everything, data, everything can be done that way. So that these are some of the advantages of digital modulation. Now let me come to constellation diagram of multi-bit quadrature digital modulation. Here we will take 2-bit example, but this we can expand to multi-bit examples. So what we are doing is we are designing the decision boundaries both in x and y. In the x we have 0, 0, then 0, 1, 1, 1 and 1, 0. X means it is I in phase quadrature, in phase q, y is q quadrature. So in phase the signal values are 0, 0, 2 bits. So 2-bit signal will be 0, 0, 0, 1, 1, 1, 1, 0. Remember this 0, 0, 0, 1, then it is not 1, 0, it is 1, 1, then 1, 0. This order you must remember, and you will understand the beauty of this order when you completely complete the digital electronics part. So 0, 0, 0, 1, 1, 1, 1, 0. Similarly, for the quadrature it is 0, 0, vertical line. You look at the vertical line 0, 0, 0, 1, 1, 1, 1, 0. That is for quadrature. For in phase, look at the horizontal line, top horizontal line. It is 0, 0, 0, 1, 1, 1, 1, 0. So accordingly, we have our boundaries. So the decision boundary, you can see 2 horizontal lines, solid lines corresponding to between 0, 1 and 1, 1. That so the which divide 0, 0, 0, 1 and 1, 1, 1, 0. So those are the lines, solid lines which define these 2 lines. Then the dashed lines are between 0, 0, 0, 1 and 1, 1, 1, 0. Between them there are dashed lines. Okay. Now from this, these are called the decision boundaries. The dashed lines and solid lines, these are called the decision boundaries. Amplitudes of I and Q, they are encoded in 2-bit digital values. Now we can view the IQ values at sample instance on a 2-dimensional coordinate system that we have seen here. Decision boundaries, they mark off regions corresponding to different data values. For example, top left, that is Q is equal to 0, 0 and I is equal to top left. If you look at the top left, Q is equal to 0, 0, I is equal to 0, 0, first line. So Q is equal to 0, 0, I is equal to 0, 0, that is the top left. Next one is 0, 1, 0, 0. Next one is 1, 1, 0, 0. Next is 1, 0, 0, 0. So those 2 bits you know. Basically we are coding the data. Mostly we use gray code. Gray code is a code, digital code, which we borrow in the communication. People also borrow this gray code. Gray coding is used to minimize the number of bit errors that occur if wrong decision is made due to the noise. Gray code can rectify that. Mostly, and gray code is the simplest code. Decoding that is done. So for decoding, if you have used a gray coding, decoding will be easier. But there is no scope of discussing gray codes in this class. Now suppose there is noise. If there is noise, you can see each of the blocks. In each block, you will see sample values no longer land in the exact same location across all sample instances. Decision boundaries remain fixed. Significant noise causes bit errors to be made, and that you can see the error has crept in. Channel SNR determines the maximum number of bits in each house, in each of the block. The channel SNR, signal to noise ratio, that will determine maximum number of bits. So that is a problem. Impact of noise, that is a problem that is to be avoided. We usually filter out the noise. There are methods, signal processing methods, to filter out the noise. So this is about the amplitude modulation, we have discussed everything. Amplitude modulation, digital modulation related to amplitude modulation, that we discussed. Now what is remaining is the constant envelope modulation. Envelope means amplitude. Amplitude will not change for the carrier. The amplitude remains constant. So this is called constant envelope modulation. Under this there are two categories. One is called phase modulation. Other is called frequency modulation. We will not discuss the frequency phase modulation. Frequency modulation to some extent we will discuss. Now, what are the issues with power efficiency in the amplitude modulation? The issues in power efficiency is you give a baseband input that goes from baseband to RF modulation. You have a modulator which will put this baseband input on RF. Then that will be amplified using a power amplifier. Remember this is very important. The power amplifier, this is what we are going to discuss later. One of the components of the modulation is power amplifier. So baseband to RF modulation, after the modulation, it goes to the power amplifier. After the power amplifier, it is transmitted. What is the necessity of the power amplifier? Unless you give sufficient power, it will not be transmitted to a sufficient distance. After a small distance, it will fade away. Therefore, you require a power amplifier. So you use a power amplifier after the modulation, because the original signal has low power. So you use a power amplifier. Then we transmit the output. So it will be transmitted. There are two types of modulation depending on what type of modulation we are using. The transmitted signal will look like either a variable envelope modulation or a constant envelope modulation. So left hand side shows you a variable envelope modulation, which is unlike an amplitude modulator, or a constant envelope modulation, which is like a frequency modulator. The power amplifier dominates the power consumption for many wireless systems. Mostly linear power amplifiers, they consume more power than the non-linear power amplifiers. The variable envelope modulation, it uses linear power amplifiers, so it consumes more power. Constant envelope modulation, they use non-linear amplifiers, so they require less power. So lower power consumption is possible when we go to on this constant envelope modulation. Lower power means conservation of energy. More energy, you are conserving energy. That is more important. So battery life will be higher. Low power consumption means more battery life. That is what we require. So that is why more people go for this constant envelope modulation. Now let us look at a simplified implementation of a constant envelope modulator. We have the baseband signal. So baseband input that goes to the baseband to RF modulation. In the baseband to RF modulation, we use a transmit filter. Why we use a transmit filter? Because we know that the baseband signal has up to this frequency, the frequency, upper frequency of the baseband signal we know. Other frequencies we don't require, those will be a wastage of power. If we transmit those frequencies or modulate those frequencies, that will be a wastage of power. So therefore we use a transmit filter first. Once it is filtered up to the frequency that is required, that has been filtered out, that we got, that will be modulated. So then we go to the oscillator, multiply that with the oscillator. Then we pass it through the power amplifier, then the transmitter out. This is basically a block diagram of the simplified constant envelope modulator. This is limited to phase and frequency modulation method. We are not going to discuss phase modulation. We will discuss only frequency modulation. Both of these can be achieved using ideal VCO. VCO stands for voltage controlled oscillator. Both phase and frequency modulation can be achieved or realized using ITR VCO. Use this as a model for analysis purpose. But remember that practically phase modulation cannot be achieved. It is extremely difficult to realize phase modulation using a practical VCO. Theoretically both can be achieved. But when you go to practice, in practice it is difficult to use VCO to realize phase modulation. So we will drop the phase modulation in our discussion. Now let us look at the constellation diagram for phase modulation. And then we will discuss the modulation, frequency modulation. Now, as you know, when you discuss about phase is actually angle. So you discuss about angle modulation of the angle. Right? And so if you discuss about angle, we usually put angle in from 0 to 360 or 0 to 2 pi. So take a circle. On the circumference of the circle, every point corresponds to an angle. So here you can see the quadrature and phase. In phase and quadrature plane, in phase and quadrature plane, we are representing the angles or phase. You start with the Q, so 0, 0, 0, then 0, 0, 1, 0, 1, 1, as I told you, then 0, 1, 0, then 1, 1, 0. This is 3 bit. So 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0. So we have divided it into how many sectors? How many boundaries? 1, 2, 3, 4, 5, 6, 7, 8. So 8 boundaries we have divided it into 8 boundaries. So 8 phases, 8 different phases. So IQ signals must always combine in such a way that amplitude remains constant. This limits the constellation points to a circle in IQ plane, as I told you, because it is angle, so it limits it to be on a circle in the IQ plane, and we can draw decision boundaries about different phase regions. Here we have taken 8 phase regions. You can take 2 phase regions, 0, 0, 0 and 0, 0, 1. You can take 4, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 4 phase regions. So accordingly you can do that. So this is, and in each sector, if it is in one of the sectors, you say that a signal comes to that phase. Now let us consider the transition between the constellation points. Constellation points are in different sectors. Now if the constellation point transits from one point to another point, how that occurs? Look at this figure. The constant envelope, this requirement will force the transition to be allowed to occur along the circle, because we have the envelope is constant. So it is only in the phase. So it has to occur along the circle. So that constellation point sits on the circle. Which circle? The circle on which the constellation point sits. IQ filtering cannot be done independently because every point has a IU and has a Q. So they are intermingled. We cannot filter them out independently. Both of them are to be done simultaneously. Then this signal significantly impacts the output spectrum, because IQ filtering cannot be done independently. So output spectrum is significantly affected due to transitioning between constellation points. So these are some of the disadvantages. Now let us come to the second. So now we will come to the multiple access That we'll discuss in the next class. So we'll stop here for today. So day after tomorrow we'll discuss about the multiple axis. And I will send you the notes so you can download the notes